All right, so in this next example, we're again going to be looking at one of these really big overall statements, and there's going to be a whole bunch of different types of quantifiers all coming into play. So there's a couple little things that have changed in this one compared to that last example. The first of which is going to be that I have this giant there exists out in front. In that last example, I started off with this universal quantifier, this notion of for all existing on the way outside, where in this case there's going to be this existential quantifier out in front. So that's going to be something that's going to change the way that this is going to be viewed. Likewise, in this case, we're also going to be dealing with two slightly different sets. The first set, where these x's are going to be coming from, is going to be the collection of all these natural numbers. So these are these nice whole numbers, your classic counting numbers. So you have 1, 2, 3, 4, all the way up as high as you can go. And on the other side, I'm going to have a set of all of the integers. And in this case, it's going to be all of those natural numbers, but it's also going to include all of the negative versions of those things as well as 0. So in this case, one of these sets is actually a subset of the other one. It's not going to have a huge ramification on this particular problem, but it's nice to kind of see the two different sets coming into play. There's no reason that both of the quantifiers have to be the same, in the same way that there's no reason that the two sets have to be the same. So in this case, I have natural numbers as well as integers. And in this case, my predicate is going to be talking about the kind of compatibility between two numbers. And in this case, that compatibility is going to be measured in terms of one being larger than the other one. So what I'm going to be looking at is x is going to be greater than or equal to y. So to start this thing off, let's actually go ahead and try to represent this thing actually as a nice, somewhat plain English sentence. What it's going to start with is going to be this notion of there exist. There's going to be some magic x in this case, and that x is going to have a bunch of properties. So let's go ahead and start with that. There exists an integer, or a natural number, and let's call that thing x, such that what powers does this thing have? It's going to have the power that for any value of y, x is going to be larger than it, such that for all integers y, we have that, in this case, x is greater than or equal to y. So let's think a little bit about what that's saying. The idea is that I can go and find a super awesome natural number. That natural number has this awesome power that no matter what integer you take, x is going to be larger than it. Well, if you think about what that's saying, it's actually saying that these integers are actually bounded by some particular number. And the answer to that is that true? And it's not, actually. The idea is that if you grabbed whatever natural number you thought was going to be the largest one, think of the largest possible number you could ever make. Well, there's always going to be one bigger than it. You could always just add 1 to it. So in this case, the idea of bounding these natural numbers or these integers is completely garbage. There's no way that you have a largest kind of upper bound to these things. They keep on going and going and going and going. They go on and on and on forever. So in terms of what this is saying kind of as a shorthand way, is it's saying that there exists kind of a largest integer, which in this case is actually false. And to see that, what I'm going to do is I'm going to try to write the negation of this thing. I'm going to first write the negation actually as a symbolic form, and then once we have it in symbolic form, we're going to go back and try to represent this thing as a somewhat nice plain English statement. So in this case, trying to negate this thing is going to have this big old negation operator on the outside, and then I'm just going to rewrite this statement. So just give me a sec to rewrite everything, and then we'll go from there. Okay, so negating these things is actually pretty easy. Again, what's going to happen is that this negation operator is just going to attack all three of those little pieces. Where it started off with this existential quantifier, this there exist, that's going to turn into a for all. So it's going to say for all x in my natural numbers. The for all is then going to change into an exists. And then the last part is going to say negate this thing on the inside. And what's going to happen is that if I'm negating this, I'm just going to be negating this notion of x is greater than or equal to y, which is actually going to say then that x is less than y. What is the opposite truth value of x being greater than y? It's going to be less than. In this case, I initially had my equality option. In the negation world, I should no longer have this equality as an option. So in this case, the negation of x greater than or equal to y is simply going to say x is less than y. So what is this thing actually saying as kind of an English phrase? What's going to happen is I'm going to have this for all now on the outside. So it's going to say for all integers, or for all natural numbers. I made that subtle change in the beginning and it's causing me more problems. I should have just left it as all integers, but what I wanted to stress is that there are these kind of abilities to have two different things. So the idea is that for all natural numbers, in this case x, we're going to have there exists an integer y such that, in this case, x is less than y. And that's true. This is actually a true statement. The idea is that give me whatever natural number you'd ever think of, I can always find another integer that's going to be larger. And the idea for that is I could just simply add 1. If you give me a natural number, adding 1 is going to give me a larger natural number in this case. So it's easy enough to do like that. And like I said, that actually gives me the counter example to what I had up above. I know that I'm not going to ever have a kind of special, awesome, super great natural number that's going to have this property that it's going to bound all possible integers. And the reason for that is because every natural number, there's going to be some integer that's actually larger than the thing you started with. So as always, be really careful with the kind of delicate balance of what the order of these things are doing. In this case, it was this notion of, is there some natural number that has some special powers? Compared to down here, it's going to be a giant overall for loop that starts this thing off saying, if you cycle through every possible natural number, can you find another number that's going to satisfy that end product?